Okay, now we have the atoms, and once we have the atoms, we have reminded the main things or the main concepts related to atoms, we must join all together to form some molecules or a crystal. Then let's remind now some basic concepts, not on the atomic structure, but about binding. Okay? First of all, we have a paradigmatic example to illustrate how important the type of bond and the binding system are. Graphite is a relatively very soft material, has somehow creamy touch. It's like oil or something like that. Diamond is the hardest known material, both of carbon. The difference, the enormous disparity between graphite and diamond is directly attributable to the type of bond, and in fact we have two completely different materials, and the properties of these materials are completely different, although the element forming them is carbon. The only difference is binding. In the case of graphite, we have these layers, which here these bonds here are quite strong, but these bonds here are much weaker. In the case of diamond, we have always quite strong bonds, so giving this material the hardness and the high transparency and all the properties. So let's go inside what happened in some details on the binding. Okay, let's consider now the binding forces. When two atoms or ions are far enough one from each other, there is no interaction between them. However, when these two atoms begin to close one to each other, then we have first the attractive force. So these atoms try to come closer, but then it reach a point in which the atoms cannot be closer to each other. It's the minimum distance they can have between them. So that is the binding position. This is here you see we have an attractive force. Here we have a repulsive force. So if the atoms approach closer, then it will repel each other. Minimum is this minimum here in the energy, of course, the equilibrium position, and is the position at which the binding is formed. Okay, let's consider these graphs in more detail. So here, this part, two atoms or ions get closer, so they experience an attractive force. Imagine Coulombian. Let's suppose, for simplicity, let us suppose it's Coulombian. It's a first approximation that works quite well. And so the system energy decreases as the atoms or the ions approach. Yeah? If they come too close, then they will start to be repelled, to repel each other, and so the system energy will increase as they approach. As they approach, the system energy is increasing. Here we have the repulsive energy. Then, of course, the net force will be the sum of the two terms. Also, the energy will be the sum of the two terms. And there will be a point, of course, in which both forces equalize. So both forces are balanced. And therefore, we have zero net force. That is the bond distance. Yeah? In the energy curve, this point corresponds to the minimum of the energy. And it's called the binding energy. Yeah? We began this lesson talking about the allotropic forms of carbon, but there are many other properties that depend, almost all the properties, depend quite strongly on how the atoms are bound to form the material, the type of bond. In particular, we are going to focus on two very important parameters that somehow determine or condition two macroscopic or some macroscopic aspects of the materials that we are going to be involved with. So one of these aspect or one of these parameters is the binding energy. Binding energy determines, for instance, the aggregation state. whether material is going to be solid or liquid or gas at ambient temperature, and it's going to determine also the melting temperature. Also very important is the cube shape. The cube shape is going to determine somehow the melting temperature also, but the elastic modulus and the thermal expansion. Let's see what it is. Here we are plotting first the force against the interatomic distance, and here the energy against the interatomic distance. So an important parameter is the slope of this curve. Yeah, is this slope. This slope is the Young modulus or modulus of elasticity. It's an indication on how easy it is to deform a material. In the case of strong bonds, this slope is much higher, so it could be steeper. And then elasticity modulus is much higher than in the case of the weak bond, because you see here the slope is much the cube is much flatter, so the slope is lower. Then Young modulus or modulus of elasticity will be the greater, the stronger the bond. Let's go now to the curve representing energy against interatomic distance. Here first we have melting temperature. Melting temperature is directly proportional or is determined by the depth of the potential here. The deepest the potential, so the most pronounced, the minimum in the energy, the highest the melting temperature. Then also, if we have a strong bond, you see here, for instance, we should make a supply of energy to a system, so that instead of being exactly as the equilibrium position, we give a surplus of energy, so we come here. So if we consider here, this corresponds to a difference in the equilibrium distance and the atomic distance, which is this distance here. If we move to a weaker bond, but weaker potential, or potential for a weaker bond, then we supply the same amount of energy, but here it should be position for the equilibrium position. But now you see that from the equilibrium position to the point in which we should be with this supply of energy is much bigger. So that means that here, for this weak bond, the thermal expansion coefficient is much larger than when the bond is stronger. Of course, there are different types of bonds, but that's another lesson.